Let's start section 2.3. Section 2.3 is functions and mathematical models. What does it mean? In this section, we are studying or reviewing actually the how to use functions or equations to model a real life problem in mathematics, solve it, and find a solution for that real world problem. It means mathematical model or models is used to find solution for the real life problems, for the real life problems. How the process works. Real life problems, some of us, we call it applications, right? The word applications is used a lot in your classes. When you go to the section that's applications, it means in that section we are handling the real life situation problems. We want to make a model for it, then solve it, then after that translate it back to a real life situation. How the process works: usually we take a real world problem, which usually given in the format of words for us. We formulate or we create a formula for it, right? Here you go. When I'm writing, we formulate. This part is the topic of studying of this section. How to change words and find maybe a function or an equation. In general, we call them a formula for it to solve it, right? To solve the problem. Then after we formulate, definitely we change it to a mathematical model. When you formulate, it means you're changing that problem to a mathematical model. After we find that model, of course, here we have to solve it. This is another part that we will learn in this section. After we created, for example, a function for a model, maybe model a function, a real life situation for your classes, you want to calculate the cost of something. First, you have to create a cost function. Then after you create a cost function, how to solve? You have to solve that cost function. After we solve, definitely we have the solution for the problem that we received in Word. Now, what we do after we solve? We are not satisfied because they are just numbers. As a student of mathematics, you may know the meaning of it, but many people around us, they are not good with math. They don't know how to translate that number to a real life. Then, this is our job. We interpret. We interpret our answer, which is a number. For example, x equal 2. Right? Or maybe you get 4,620. What does 4,620 means? You have to translate that back to real solution of real world problem. solution of real world problem. This is the process that we are learning in this section. Picking up a problem from real life, find a formula for it, solve it, translate back to the real life situation. To do this, I will go back a little bit in your previous algebra classes. I will talk about some functions that we are using it a lot to create these models. The first type, we call it polynomials. Now, what is a polynomial? You already know, but to review it, I will write the general form for a polynomial, and I'll just write a few numeric examples of it also for you. Any function, if I name it f of x, that's in the form of a n x to the power of n plus a sub n minus 1 x to the power of n minus 1 plus we continue this way to get a sub 2 x to the power of 2 plus a sub 1 x to the power of 1 plus a 0. We call that function a polynomial function. Few numeric examples. For example, f of x equals 2x plus 1. That's an example of polynomial function. Or f of x equals x squared plus 7x plus 10. That will be an example, another example of polynomial function. Or f of x equals 5x to the power of 4 plus 2x cubed plus 3x minus 1. That can be another example of a polynomial function. In general, what you see in all these examples that I just noted for you, you can see few things. If you remember in a previous lecture, in the lecture before, I explained to you in a very easy language that if you don't see a root, a variable under a root, or if you see a variable with rational exponent, or if you have a variable in denominator, you cannot call those functions polynomial. If I don't have this three, then I can call my function a polynomial. Now, we got some knowledge what's a polynomial function. You see they are like different powers. For example, example number 1, the power of x is 1, the highest power is 1. In example number 2, the power of x, the highest power of x is 2. In example number 3, the highest power of x is 4, right? They have different powers. At least here, I'll try to cover two main types of them that you will see during the semester. The first type, we call it linear functions. Linear functions means the highest power of your variable, which I named it here x, is 1. The general form for a linear function is f of x equals mx. I'm using this form because most of you are familiar with, you saw it before, f of x equals mx plus b. Here, m and b are numbers, and x is variable. Great. If I put a numeric example, another one for you, for example, f of x equals 3x plus 6. You see that m is equal 3 and b is equal 6. M and B, they are integers. They are numbers, not all the time positive. I should call them integers. They can be negative, right? Negative and positive numbers. They are just numbers. Now, why linear functions? First of all, let's talk about the graph of linear functions or linear function. As you see the name is linear. The graph of a linear function is always a line. Correct? If I just draw one example of it, this is x-axis, this is the y-axis, and maybe I'll draw this line and I'll name it f of x. This will be the graph of a linear function, which is a line. Correct? A line means every line that we are drawing, it has a slope. Right? It has what? A slope. Now, what is slope? Most of you know a slope means rise over run. You studied in your high school or lower classes of mathematics at college level. Slope means rise over run. For you, or the actual, not just you, the actual meaning of slope is slope for us in this book means rate of change. Many of us, we have this problem. We start drawing lines, graphing lines in lower classes of algebra, even during the school time. But it's always introduced to us as a slope of the line, slope of the line. Barely we could get the meaning of it, that why slope, what is slope? Okay, the meaning that they gave us, it's rise over run, but the actual meaning where we use it and how to use it in real life, why I'm studying is because slope means rate of change. Now, for the lines, the slope is constant. Constant means it's not changing. It's really an important note for you. I'll put a star here, that for linear functions, the slope is always constant. It means the rate of change is constant. Slope constant means rate of change constant. Why we are focusing too much on this? Soon you will see I'll start with some applications of business that I will use rate of change in it. I'll create a function for it. We will do it together. We will solve the function, and there we learn where we use it in our class. Correct? Let's start from this. Let's first create one more time. I know you did it so many times. Let's find one more time the slope formula. What is slope? Let's choose on this red line one point, name it x1. Of course, here on the y, the coordinates will be y1. If I pick another point on the line, the value of x, I'll name it x2. Of course, here on the y, the value will be y2. What I'll do here, I'll try to draw this right triangle for you. Great. And this right triangle, the distance from x1 to x2, if you calculate mathematically, it will be x2 minus x1. The distance between y1 to y2, definitely this distance is y2 minus what? y1. Now, the distance from y1 to y2, actually that's the rise. And the distance from x1 to x2, this is your run. If I substitute in the slope formula these values, I'll use m as a notation for the slope. Most of you are familiar with that m in this topic represents the slope. Then m equals rise, which is y2 minus y1 over run, which is x2 minus x1. This one will be your slope formula. It means, what does it mean? If I know 2 points on the line, x1, y1, and x2, let's name it in general, y2, if I only know 2 points on the line, I can find the slope. And slope for me means rate of change. Correct? And I can find easily the slope. Why slope? Because we want to find the rate of change. And let me tell you, if we know the slope and 1 point, even 1 point, for example, x1, y1, we can find the equation for the line. How? We will use the point slope formula. I will just write the formula here for you. There is a proof behind from where this formula comes in. Because your class is not required to learn the proofs, I will avoid that proof to save some time also for you. And to be honest, this formula, you see it so many times in your life. The point slope formula is y minus y1 equals m times x minus x1. We call this formula point slope formula, or this equation we call it point slope formula. You see, in this formula, if you know the slope, if you know only 1 point, which is x1 and y1 of a line, if you plug in those numbers in this formula, easily you can write the equation of the line. For the linear functions, I'll just do right now 2 examples, one numeric example and one application, because later in chapter 3 and 4 we will do a lot of applications. This is just the review part of your book, which we review here, Algebra. I'll just go over 2 examples, and after that we are jumping, and I'll introduce at least one more types of these functions. Okay. Example number 1. In this example, they are asking you, find the slope of the line passing from -2, 4 and 6, let's say 8. They're asking you to find the slope of the line. 2 points is given to you. Copy your slope formula. M equals y2 minus y1 over x2 minus x1. To make it easy, I'll name the first parenthesis the first order pair x1, y1, the second order pair x2, y2. It doesn't matter for you which way you name, right? You can name the second order pair as a x1, y1, the first order pair as x2, y2. It doesn't matter. But please do not change, do not name, oh, I'll name 6y2 and I'll name 8x2. We can't do that because we know that an order pair is always in the form of x comma y. Correct? Anyway, let's plug in those numbers in the formula. M equals y2, which is 8, minus y1, which is 4, over x2, which is 6, minus x1, -2. It means 8 minus 4 gives you 4. 6 minus -2, double negative becomes positive. It means 6 plus 2, which gives us 8. If you reduce, it will be 1/2. It means the slope of the line is 1/2. It means the rate of change in that line is 1/2. Correct? This is how we do. If right now they ask me to write the equation, definitely I can write the equation, but I'll show that one in the next example, actually a real life situation, and you will see how you can create even a function. Example number 2, let's copy an application here. In example number 2, I have a problem for you. It says, it costs a publisher $400 to print 60 books. And it costs $760 to print 120 books. In this problem, they are asking you, find the rate of change here. Rate of change for us means, I will write it down, it's not given that way. They are just asking you find the rate of change, but rate of change here for us means the slope of the publishing cost function. It means we are looking for the slope. Assuming it is linear function. Okay, let's start. If you read the problem, you will see actually they are giving us two order pairs. There are two quantities are here involved. One of them is books, and the other one is cost. 60 books cost $400, and 120 books cost $760. Do you see you get two order pairs? To find the rate of change, it means to find the slope between these 2 points, then m equals y2 minus y1 over x2 minus x1. For us, here y represents the cost, right? It means m equals y2 760. If I name 120 x2, 760 y2, $760 minus $400 over 120 books minus 60 books. 760 minus 400 gives you $360 over 120 books minus 60 books gives you 60 books. If you reduce, it gives you 6. What is the 6? This is $6. Correct? What does it mean that $6 actually for us? It means each additional book costs $6 to publish. If I complete my sentence, $6 to publish. It's really a great information. It's really a great information. For example, you're running a printing business or publishing business. Of course, here I use the model of a linear in this example. If somehow you end up getting a model of linear, easily you can have a function. Easily you can calculate how much it costs you. Correct? Let's create a second part for this example. And the second part of the example, I'll name it part B. Let's say, find the cost function C of X. Usually, we name our cost function C of X. Okay, here I will use the point slope formula. Y minus y1 equals m times x minus x1. Y minus y1, I'll use the order pair 60 books cost $400. I'll use that one, or I can use the other one. Both of them gives you the same equation. Y minus y1, which is 400, equals m, the slope we just calculated at 6, times x minus x1, which is 60. Y minus 400 equals, let's distribute the 6 to the inside, 6x minus 360. Let's move that 400 also on the other side. Add 400 to both sides. Then y equals 6x plus 400 minus 360 gives you 40. This one will be the equation for the publishing line, because we see this equation as a cost function. Then I can rewrite, just replace y with c of x. C of x equals 6x plus 40. Remember in lecture 2 or lecture 1, during the lecture, I explained two things for you. That a cost function has two parts, variable cost and fixed cost. For us, here, this thing will be your 40 will be your fixed cost. And 6x is variable cost. You see? Now you have the function. If I add another part for this problem, part C, find the cost of publishing $200 books. It's so easy to calculate because you have the cost function. Your cost function is C of x equals 6x plus 40. Again, if I go to first lecture that we learn how to evaluate a function, here you're looking for the C of 200, the cost of 200 books, which will be equal 6 times, replace x with 200, plus 40. It means the cost of 200 books will be equal to 6 times 2 gives you 1200 plus 40. It means the cost of 200 books will be 1240. Definitely the unit for us will be dollars. Correct? This last example, the application that we did here, actually it explains to us why we did this. It explains to us that we are using mathematical models to solve the real world problems. And easily you saw that here, that I used a linear model to find the cost function if I know the rate of change and my function is constant. Correct? To do not make this lecture too long for you, I'll stop the lecture here, but I'll make a second part for the lecture. Maybe in that part we cover some models of quadratic functions. First, we know what's quadratic. And also maybe we will cover some kind of problems that we start from scratch, from nothing. We build a formula, then we solve the actual modeling, right? I'll stop the lecture and see you all in part 2 of section